Okay, so to remind you, we're considering the Gross-Spithievsky equations, and our goal is to prove a theorem about dynamics of vortices. So to recall the notation, for example, J star will denote the velocity field generated by J star with, say, parameters C and D will denote the velocity field in my bounded domain generated by point vortices at points C1 up to Cm with a multiplicity D1 up to Dm. We're going to assign an energy to that, or renormalized energy. And then there's this construction which gives what we can then later verify is a wave function psi who's essentially energetically optimal given vortices at these points. And so there's expansion of the energy and involving exactly this W above this renormalized energy. That's sort of so the energy has this divergent part here, and this is the leading order finite part. Okay, so that's that. Then if we want, we could write an explicit formula for those things. Our goal is this theorem, which says, actually I'd written the equation wrong in every previous lecture, which didn't matter because I didn't prove anything about it until now. So now I'll actually need to get it right. I've omitted these numbers and this factor of 2, which I think is supposed to be there. Okay, so we consider, so this is a theorem that says that if we have a solution to Gross-Spithievsky equation with vortices at some initial locations, with some initial degrees, and whose energy is as small as possible asymptotically, given this information vorticity. If we have, say, a sequence of solutions, then the vorticity converges to point masses located at points A, M of t that are found by solving the point vortex ODEs with a factor of 2. The factor of 2 rises because, for other reasons, I put a factor of a half when I define the vorticity. So that's that. And then we have these tools, which we spent quite a lot of time discussing. So we began the proof of the main theorem last time, and we're just going to finish it today. And so we proved these various things. We proved that, so the main, so claims 1 and 2 were leading up to this claim 3, which says we can, if we fix this time interval t naught in which nothing moves very far, and we prove that we can select a subsequence, say epsilon sub k tending to 0, such that if we let epsilon k, if we consider the subsequence where we fix any time t, the vorticity at that time t will converge to these delta function sets of points bm of t, where these bm of t are elliptic continuous paths. So this is a compactness assertion. And then we also argued that having fixed the subsequence, the currents little j of psi epsilon converge weakly to the what is at time t, so weakly in dx dt, to the current that at time t is exactly the one generated by the vortices at the points bm of t found above by this compactness proof. Okay, and so this is where we are so far, and we just have to prove. In fact, I'm going to prove for claim 5. I'll prove an integral form of this assertion. I'll prove that am at time t is bounded by the integral from 0 to t of, well, okay, let's write it. First, I'll introduce this notation. So the thing I want to control is this, and let me call that zeta of t. Okay, and so we've found these paths bm of t. Our assumptions imply that bm at time 0 is exactly the point a sub m 0, the initial point. There should be no t here. Or no, sorry. When t is 0, bm at 0 is exactly a m 0. There should be no superscript here. Yeah, these are supposed to be the initial locations in both of these assertions. Okay, and so the AMs solve ODE. I fix a time so they don't move very far, and the BMs also I can arguments above I can arrange they don't move very far in time to not. Okay, so so this is just sort of summarizing what we know. The main point of this is I want to draw a picture. So we have these. I'll just draw a picture around the mth vortex, and so here's what it looks like. So we have some initial location A, M, 0. And then we have these paths A, M of t that we obtain by solving the point vortex ODEs. And so elsewhere off the frame of the picture, off stage are other vortices and their generating flows and so on. We also have these paths, say, in a different color. B, M of t Lipschitz continuous paths that we obtain by this passage to limits and so on by getting some estimates and using these compactness things. Okay, and then for every epsilon, actually, we can find a path, say, it doesn't even have to be continuous, C epsilon of t. So the point is, for every time t, I can apply this vorticity. So these b sub m of t's are obtained by passing the limits. If I look at a positive epsilon, then I can obtain my localization. I can apply my localization theorem and find that the vorticity at time t for this epsilon value is localized somewhere, and what the assertion about the b sub m says is that these bm of t are the limits of this. Bm of t is the limit of the xc of t. Okay, so unfortunately, I have to worry about both the limiting location and the epsilon location. And so then, right, and so by applying the localization theorem again, I know that at every time in the interval I'm considering, the vorticity is well localized about some points xc epsilon m. I needed it. The vorticity is localized at these points xc epsilon m, and because the vorticity is converging to these points b to t, and the xc's are also converging to the b's. Okay, so this is the picture, and all of this is inside. Let's see. And all of this is inside some balls. Maybe this is, rho sub a over 10, and this was rho sub a over 5, something like that. Okay, and so and so these balls have the property that, if there are other vortices over here with a similar picture, all these balls will be disjoint. Okay, and so this is our picture so far. And right, and so we know that, right, so this is the assertion that as shown in the picture. The distance between CM and BM tends to 0 as epsilon goes to 0. So whenever I have an arrow, this is always implicitly as epsilon goes to 0. And thus the distance from CM to AM is like the distance from CM to B, from AM to BM, plus small errors, right? And so CM minus AM, the sum of those is basically the sum of BM minus AM, which is zeta, up to small errors. Okay, so here's the idea. The idea is, well, Okay, I'm going to use the identity for the evolution of the vorticity in integral form. ddt of a test function times the vorticity is this combination of derivatives and so on and so on. I'll use that. And the point is this: we know from Theorem Two. Well, so what do we know? We know from let's look at Theorem Two, which is up here. So I want to apply this to. I want to think of psi being psi epsilon of t, a solution at time t of the equation. And I know that at time 0, and I'd like to think of this as being, say, the points c epsilon at time t, and this is, which is basically the limiting points. And I'll use this being psi epsilon at time t. And so what I want to know, I'd like to know that this stuff is small. Then I know a lot about what my wave function psi looks like at time t, and I can use that information. To know that I have to know that the left-hand side is small. And what's the left-hand side? Well, this. So for the PDE, the energy is conserved. So I know what that is. And I've also made assumptions about the initial energy. I've assumed that the initial energy is exactly what I need to manufacture vortices at the initial locations, and plus a term who vanishes as epsilon goes to 0. Okay, and so this is, it's like m times pi log 1 over epsilon plus this number gamma I keep on mentioning, plus the energy for the initial vortex locations and degrees, plus terms that vanish as epsilon goes to 0. This, on the other hand, is, well, it's m pi log 1 over epsilon plus gamma plus w of b at time t. Okay, and so, okay, and so I'd like to write this as the difference of this in w of a at time t. So remember here, a are the trajectories found by solving the ODE. Okay, and then and so this is some error which is controlled by the distance from the B's to the A's. And this again, by conservation of energy, is W at A of 0 and D. So I have conservation of energy of both the PDE and the ODE. And so, okay, let's go. I think I wrote this down here. Okay, and so so here's the point. I have conservation of energy for the PDE and the ODE, and so if the vortices are exactly where they should be, so initially there was only enough energy to manufacture those vortices, those positions. If at time t the vortices are exactly where they should be, then there's still exactly enough energy to create those vortices or those positions. If there's any extra energy, if the energy of the wave function is too big compared to the energy of the actual vortex location, so these A sub m's are the desired locations, these B sub m's are the actual locations. It's possible the B sub m's have moved a little bit to a place where where it's less expensive to create those vortices. And then the extra energy in the system, the surplus energy, will be exactly proportional to the the amount they've moved. So Here it is. So this W of C may be less, may require less energy for vortices by this amount, which is proportional to the amount moved. And so the conclusion is that the if I compare the energy of the PDE with the energy of vortices location is B, that's bounded by this, and that in turn controls the left-hand side here. Okay, and so so everything I want to control is estimated by how far the vortices have drifted from the positions where I would like them to be, which is what this zeta of t measures. Okay, good. So that's what this tells us. That's what this picture is supposed to remind us of. Okay. Now, henceforth, I want to fix a time t between 0 and capital T. And I will fix a test function phi. And let's go back to this picture. I want to fix a test function phi so that I have the zeta of t. Well, it's probably a bit irritating, isn't it, if I move this around wildly when you're looking at it. So I want zeta at t, the sum of b m of t minus a m of t, absolute value. I think I have a factor of a constant pi here. I would like this to be, say, phi. Well, here's what I do. I fix just a vector, the vector from, and there's a, I think there's a, I fix a vector from AM to BM or vice versa, a unit vector pointing that direction. And I choose a function whose linear inside here. So here I'll choose, and then here, you know, the supportive phi is concentrated out here as usual. So or the support of the second derivative is in this analysis. Okay, and so then if I look at phi of B minus phi of A, sorry for the colors, that will be exactly B minus A plus the dot product with the vector joining them. So that will give me the you know, the modulus of the vector of B to the minus A to them. Okay, and so in this way I can fix a test function phi so that okay, so the supportive phi is in the larger ball, phi is linear in the smaller ball, and okay, its second derivatives are bounded in this way, and I can and so here what I'm asking is for this to equal plus or minus b sub m minus h. And I have a sign here for that's convenient. Okay, and so the point is I can obtain this function zeta of t, the sum of the distances from between where I would like to be and where I actually am, where the vortices should be and where they are. I can obtain that by evaluating this fixed function phi at these points. Okay, and then furthermore, I would like to okay, well, I'm doing this in a way that may seem more complicated. I'll tell you why I'm doing this in a second. But what I want to get to is this down here at the bottom. So I'd like to evaluate zeta of t by you see, well, here it is. Okay, let's just say it. Okay, so up here I have this. This is essentially the definition of phi. If I look down below, I've added and subtracted these things, and those are equal because b m of 0 is equal to a m of 0. Okay, and so I haven't done anything, But now I can each of these is a difference between some quantity times t and some quantity times 0. And so I can obtain that by integrating from 0 to t of some time derivative. Okay. And so, right. And so this zeta of t is, well then also finally, so here's why okay, look at this. Phi, if I look at phi evaluated at this points b of t, that I can obtain that by multiplying phi against the vorticity, omega epsilon, omega, the vorticity of psi epsilon of t, and then letting epsilon go to 0. Because exactly that's the definition of b's. These are the places where the vorticity concentrates, and these d's are the signs of those places. And so the fact that the limit of epsilon goes to 0, these vorticities are these sum of delta functions at the points b, m with degree dm, allows me to, is what gives this identity. Okay, and so here I have a limit here. The limit, of course, doesn't matter in the second terms. Okay, so so finally, this is what I wanted to do here. I can then write this difference of the integral phi times vorticity at time t and at time 0. I can write that as an integral of a derivative of the time derivative. I've changed it. I've given it a new name because it's a dummy variable. I write this thing as the integral of a derivative, and then I know, and then I'm able to use my formula for the time evolution of the vorticity, which is here. Okay, so in the end, it comes down to integrating or to estimating this integral. And let me see. You see, I could have just said, well, I want to compute. Well, the point is, I could have just looked at this would look more reasonable. I'm comparing the evolution of vorticity against the evolution of the limiting paths at a fixed time t. It'll turn out that we need the time integral for reasons that we can have in a moment. So I had to go to this preliminary argument, but we're really comparing the time derivative of the vorticity and the time derivative of the limiting paths. Okay, which is very natural. And so my goal then is to understand this integral. And let me first look at the this piece. Okay, and so for simplicity, I'll write j sub epsilon to be the current associated wave function psi epsilon, and now everything is fixed at time t, or some time. Maybe I've called it. I guess I called it t. I should have called it s. So we're thinking of fixing this at some time. I'm integrating from 0 to s, and I had to I called it t by mistake. Okay, so as we've done before, I can write the gradient as the sum of a component in the direction parallel to psi epsilon and in the direction orthogonal to psi epsilon, and this is exactly what I get. And so then expanding this as we've done before, I'll find that. So remember, this is this nabla psi tensor nabla psi that is a 2x2 matrix whose ij component is the dot product of the ith and jth derivatives. And so this is what I get. If I carry out this first computation, because using the fact that these I psi over psi and psi over psi, that these are orthonormal basis for R2, if you like. And then I write, so from here to here, I write j epsilon to be So remember, J tilde is the limiting thing. J tilde is the current generated by vortices at the points B of T at the locations obtained by this passage to limits. So I write this in both of these factors in this way. So I'll get 4 terms. I'll get a J tilde tensor J tilde, a term involving the difference tensor the difference, and then I get cross terms. Okay, clear enough. And so, so I then want to multiply all this stuff by this combination nabla perp of phi, and then let epsilon go to 0 and see what happens. Okay, and so I'm going to make 3, and so I end up having to look at these 3 terms. And so I'll make 3 claims. And I'll go, so the first 2 I'll go over kind of quickly, and the last one, well, actually we'll go over everything kind of quickly. But the first claim is that these terms here and here are estimated by this function zeta t. They're, in other words, if the actual vortex locations are close to where they should be, then these terms are small. Then my next claim is the second one, the cross terms. These just vanish as epsilon goes to 0 once I integrate in time. And then the third term will give us something non-zero, which is related to exactly the PD, sorry, the ODE, the point vortex ODEs. So these are the 3 claims. Let's see why this is true. Okay, so I'm gonna do this here. Sorry for the mess. So okay, and so this is bound by the L infinity norm of this thing, and then the L2 norm of well, okay, it's integral over the support of d squared phi of this, and this exactly is what we said a second ago. Where did we say this? Here we said it. This is small if this is, so this is what's controlled by Z. Okay, actually there's a little so down below I had a J tilde, which is J star of B of T D, but it's not hard to replace this by that and maintain this estimate. Okay, so I'm kind of glossing over some details here, but but the point here is that you know, I'm adjusting this J tilde to J star by a small amount, and I'm integrating over the set which is bounded away. It's bounded out here. That's where the support is, and so that's not going to make a difference. Okay, good. So that's the first claim. And so again, if the vortices are where they should be, there's you know, we know a lot about what the wave function looks like, and so we know that the modulus has very small energy, and that the phase is very close to the phase generated by those vortex locations, and the extent to which this fails is quantified by this number zeta. Okay, second term, and here's where so we're considering this done. So I'm sorry, I'm going kind of quickly because we're out of time. Second term. So we already know we know that this is true. But here's where I need to integrate in time. So I have the J epsilons converging to this J tilde in dx dt in the space-time domain weakly. And so, okay, here I don't quite have J epsilon. I have J epsilon over psi epsilon. But okay, well, what do we say? We can fix this. And so let me say this in words. We also have uniform bounds on J epsilon over psi epsilon. So we know that that's if I stay away from that's diverging in L2 at the vortices. But away from the vortices, it's uniformly bound in L2. So in particular, in the support of this integral, this J epsilon over psi epsilon is uniformly bound in L2, and so it converges to a limit weakly in L2. And the norm of psi epsilon converges to 1 in L2. And so by messing around with these things, you can see that J epsilon over psi epsilon and J epsilon, if they're both compact, if they're both converging weakly to some limits, then they have to be the same limit by using the fact that the norm of psi epsilon is converging to 1 strongly in L2. Okay, and so we can deduce J epsilon over psi epsilon converges to the same J tilde. And this is away from the vortices, so to speak. But here my integral is away, and so here I'm multiplying. Say if I look at this term, I'm multiplying this difference by, well, these things are away from the vortices. They're just perfectly smooth functions. They're fixed smooth functions. And so the definition of weak convergence tells me that I can pass the limits in this expression, and the limit of this is 0. So okay, and so here we're using weak convergence together with, and so here again we're also using the conservation of momentum, which tells us that this is how we proved this. We said that the divergence of the momentum was d dt of the modulus, and d dt of the modulus is very small in some negative norm. And so this allows us to conclude that the divergence of, so we had other, for other reasons we knew that this J tilde existed. And then we could conclude that J tilde is divergence free and has vortices to the given locations, and then that characterizes it. Okay, and so the last thing is this, which is, let's say it's just a computation. Here's how the computation goes. So we'll do this in more detail. And so let's write, again, if I have my picture. Okay, so I'm going to let A sub m of s comma t, A of m s t, A stands for annulus. It's not quite an annulus, but it's the big ball around A sub m, around the initial location. And then I subtract a ball of radius s, and I want to think of s as being very small, around the point where the vortex is at a given time t. I'm sorry, my notation is kind of awful. I was using s to mean something else a little while ago. So sorry about that. Okay, and so I claim first that the integral of this integral I have to evaluate. This thing is the sum of the integrals over these regions. And the point is, well, you know, the integral is supported in these larger annuli out here. And if I want to, I can integrate over, you know, I can squeeze down on this. I can subtract a smaller ball around a ball of radius s around the point B sub m. Okay, so that's clearly true. And then oops, so let's remember this. Remember the picture. Okay, and so then right. So this is true, and then here I've added the identity. So this is a 2 by 2 matrix. I've added a diagonal matrix, a multiple identity. And so the point is that this thing, we've seen this before, this gradient of nabla perp phi by its structure is symmetric and trace free. And so it's Hilbert-Schmidt inner product with the, sorry, it's trace free. And so it's Hilbert-Schmidt inner product with the identity matrix at 0. And so I've just added 0 here. But the point is, maybe I should, let me write this out a little bit. Well, here it is. So down below, I've written out what this means in detail. So here, epsilon AB is 1 if A is 1, B is 2, minus 1 if A is 2, B is 1, and 0 if the two indices are equal. So it's an anti-symmetric tensor. So okay, and so and I may have some signs wrong here. I hope not, but I think this is right. Okay, and so if we write out this this expression in terms of components, here's what we get. And so I want to integrate by parts. I move the partial sub c onto this expression. And here's where I claim it's divergence free. So if I differentiate this, I'll get a partial sub c of j tilde sub c that vanishes because j tilde is divergence free. I'll get a partial sub c of j tilde a times j sub c. And that exactly is the same thing I get if I differentiate this delta AC j tilde c with respect to c. So that's so the divergence of this is 0, and I can then integrate by parts, and I'll just get a boundary integral. Okay, this thing times the normal, the c component of the unit normal, and okay, there should be a minus sign someplace, but you see the outer normal to this region A is pointing inward with respect to the ball. And so here I have the outer unit normal to the ball, and so the minus sign is absorbed by that, if I've done this correctly. Okay, and so then, well, the point is just that we can, so again, this j tilde, we know exactly what it is. It's the velocity field generated by the point vortices at these points B sub m. And so we know that it diverges near, so I want to, again, consider the mth integral. And we know that around the mth point, this j tilde has a divergent part, who's this rotational thing. And I'm missing a sign d sub m here. And so we have that, and then there's a regular part. Just everything else, the difference between the velocity field and the divergent part. And so we just substitute this into this expression, And so then these, we get a bunch of terms. The leading terms will all cancel because of symmetry and antisymmetry. So that, and then you just do some calculations. And the point is that this this regular part, if I evaluate that at the point b sub m, for example, which is so when I let s go to 0, I crush down on the point b sub m. And so I'll get, I'm getting this regular part evaluated at the point b sub m with some constants. That's what the calculation gives us. The regular part is exactly the, the flow generated by the point vortex system, because that's how we get that. We look at the velocity field obtained by the BO sub r kernel, who is exactly this j tilde, and then we subtract out the divergent part, which we say it's purely rotational, it doesn't have any impact on the vortex motion. Okay, so if we do this computation, I claim this is what we get, and there's a factor of 2 pi from, you end up integrating around this circle of radius. You get a 2 pi s from integrating around the circle, and then a 1 over s from here to now. Okay, so calculation details are made. And I think that's, okay, so here's the conclusion. Then, so this zeta of t is an integral from 0 to t of this thing we've just integrated, we've just estimated of this expression. And this should be exactly grad perp of w at the point a of s with the fixed degrees d, the mth component of the gradient. And there's a factor of 2. And there's a d sub. Well, yeah, that's I think there's a d sub m. Right. Yes, there's a d sub m up here. Okay, good. So so we've just evaluated this, so there's all this stuff who's estimated by this zeta of t, and then there's something who's exactly 2 d sub m now the purpose. So what we get is, I forgot the d sub m's again. Okay, so if we put this together, here's what we get. And then the point again is, well, this is bounded by the second derivatives of w at some point times b of s minus a of s, so to speak. And in each case, you see this w could be kind of bad, but in each case, I'm just moving the points. So this vector from the a sub m to b sub m is small, and so this in fact is okay. It's bounded. And so the whole thing then is estimated by the sum of the okay, maybe I should have put a sum over m, and m is here. Okay, but the whole thing is estimated by the same number zeta, and so I have this inequality, and from this I can conclude that zeta of t is less than a constant times e to the ct times zeta of 0. This is a form of Grom's inequality, and this is equal to 0 because zeta vanishes at time 0. Okay, and so that's the proof very quickly. I had to rush to get through it. And let me see. I'd wanted to, but what can we say? Okay, so there were a lot of details to keep straight. But the philosophy is, well, yeah, as we set up here. So what this tells us is, if the vortices are close to where they should be, then the velocity that we obtain by using using this identity, if the vortices are close to where they should be, then we have a lot of information about this. We know exactly what this is up to errors, and the size of the errors is proportional to the deviation between the actual vortex location and the ideal vortex locations. If the vortices are close to where they should be, so we can then estimate very well how this axon test function, which is the so it's like the distributional vortex velocities. Okay, and if the vortices are close to where they should be, then the errors in this computation are proportional to the deviation from where they should be, because yeah, that's and some of the main point is this use of Theorem Two to say that any extra energy in the system controls these norms. So if the phase differences, well, yeah. So again, we rely crucially on this. Okay, so tell you what. So I promised that this would be the last lecture, and so what I'll do, however, is I'm going to consider Wednesday sort of a office hours or drop in or something, and because I wanted to talk about, you know, if you're young and you want to work on questions of this sort, what are good things to work on? And so if anyone's interested at all, I'd be happy to talk about that on Wednesday, just for, you know, just to kind of talk in a very general and non-technical way, and to give an overview of the stuff we've done. The greatest thing I should have done and didn't is, so I had this plan, and the thing I really failed to do was anything about, so there's a different family of techniques for these problems, especially for order equations that have been developed quite recently and are very powerful. And so these are these PDE techniques based on gluing arguments these were first developed in the elliptic PDE setting, and recent work of, especially of Davila, Del Pino, Musso, and Wei have proved, so they proved this, they're giving a construction of leapfrogging for the Euler equations. So I didn't do any of that, and I should have, but you know, there's only so much time, and so that's the thing we didn't cover, yeah, that's a very powerful and promising technique. It's hard to compete with those guys because they're a big team, and they you know, they have all these experience from related elliptic problems, and so they are likely to prove a few more theorems before they stop, and who knows what those theorems will be. But there are other things to work on, and I may discuss those a bit on Wednesday. For now, let me stop and see if there are any questions, and I'll also upload this here. But so, well, actually, let me make one more remark. Well, no, I mean, so you can see what I actually proved just did. We called this zeta of t. We said zeta at time t is bounded by a constant d integral from 0 to t of zeta of s ds, which is say it's the integrated version of the same statement. And we needed that because we needed to use the weak conversions in spacetime dx dt of the currents j to this limit, who we knew exactly. And we needed to use this claim 4. Okay, so if there are any questions, I'm happy to try to answer them. And in the meantime, I will upload this. Okay. Okay, so that's there. And back to the. Okay, and so yeah, so a question was, what did I say about Del Pino? Can I say it again? So the let's do this. So the so not covered. So the most important topic not covered is what's called gluing techniques. And this is due to, this has been developed in the recent years by Davila, Del Pino, Musso, and Wei, starting a few years ago and continuing through their work on these things now. And so the idea would be, is I have, you know, say omega sub t plus u dot grad omega. Okay, so I have the Euler equation in some form, and so we would say we would construct some approximate solution. Say, first I think of some behavior I want to show. I think of some kind of phenomenon I'd like to prove the existence of. So, you know, a solution of Euler with vortices moving around in a certain way, who knows what. And so I construct an approximate solution with the desired behavior. So, you know, omega epsilon of x and of t and x is who knows what. So you construct it somehow. And then this means such that, and say u epsilon is so dt of this omega epsilon plus, well, okay, maybe not. Let's say this. And u epsilon minus the p is for our kernel. So, you know, I might make it be some power epsilon to, you know, the epsilon to some power k. And I might want to say its derivatives are small. I mean, so you construct something. And then we seek a solution. Of the form, say, okay, let's call this omega tilde. Say omega epsilon is omega epsilon tilde plus phi epsilon, and u epsilon is u epsilon tilde plus I don't know what sigma epsilon, and then we get a PDEs for phi epsilon and sigma epsilon, and so I just substitute these into here, into star, and I get a new system of PDs. But the advantage of this is that now, okay, so if I can do this, so my goal is to find small solutions. And so this would mean this means I've found solutions who have the desired behavior with the small corrections. Okay, and so then so the advantage of this is that it converts this PDE problem from a large data problem to a small data problem. So in general, finding small solutions is easier than finding big solutions. You can that's the principle. And then also one often has some information about spectral, about, when you do this, you get a linearized equation, and you may know something with the spectrum of a linearized operator from elliptic problems or something like that. So that's what they do. And they did this first. They gave a new proof of the Marchioro-Polverenti theorem, on which we proved on vortex dynamics in the plane. And in some ways, their result is weaker. They may have much stronger. Well, they have much stronger hypotheses and a much more precise description of the behavior of the vortices that they construct. But then they went ahead and gave a proof of this leapfrogging vortex phenomenon, and they've constructed certain rigidly rotating solutions, and they're probably working on more things. So that's so I'd hoped to have time to do this argument in a kind of a relatively simple setting, but I didn't. So that was that. Okay. Other questions? Okay, well, I'll wait around for a couple of minutes in case you think of anything, and let me say, this. I think Fabio Pusatteri's lecture, his other class, may be meeting on Wednesday, and so this this class is over. It ended Friday, but so this Wednesday I will be here. Just this is just for say for fun, for entertainment, and also office hours are, I guess, over at this point. But if students in the class have anything to discuss with me, then please feel free to send me an email or get in touch somehow. So, okay, so that's this.
Hello.
Hi.
I would have a quick question if no one else does. And what I didn't understand, what I would like to ask is this approach by Davida del Pino Musso. So what it seems to me that is they construct one solution exhibiting this desired behavior like leapfrogging or whatever, depending on the scenario, while your result really gives kind of a notion of stability. No, once you have the concentrated vorticity, then all solutions should behave in this.
Yeah. Yes and no. I mean, there are a lot of. Well, let me show again this screen. So what they show in the end, hold on. Okay, and so what they show is that they get an equation for these things, and they show that and so there's so they show they construct they show that for any essentially they have you know, or rather they have they find epsilon 0 and sigma epsilon 0 such that the corresponding so that the solutions phi epsilon sigma epsilon of this equation for the perturbation exist for some fixed time t and remain small. But in fact, this construction is robust with respect to small perturbations. And so if you look at something close to this in a strong enough norm, close enough in a strong enough norm, then it'll have the same behavior. And so it's like a small open set in a strong topology. Whereas in fact for Gross-Pitkevsky, I mean, I would say for the Marchioro polarity has quite a strong notion of stability, but they also require so that's in a way the more natural one to compare to the Davila et al. Group, because it's the Euler equations. Marchioro polarity have a much stronger notion of stability, and they allow actually pretty crazy initial data. It can be very big, and it can have infinite energy, or say energy that diverges to infinity very rapidly as epsilon goes to 0. Like that. But right, they have strong stability, but they require the vortices to be compactly supported. This is what they really require. Whereas in the Del Pino et al. Construction, the vorticity is actually not compactly supported. It's small but non-vanishing away from the concentrated vortices. So each one has its advantages. I mean, I would say so far the big advantage of the approach of Del Pino and Davila is that they can analyze situations that are so far out of reach for other techniques. Yeah.
Thank you.
You're welcome. Okay, good. So then I will sign off, and you're welcome to come on Wednesday or not, as you choose, and otherwise.
Yeah, unfortunately on Wednesday I will be teaching on this lot of time, so I won't be there on Wednesday and bother you with the questions.
Well,
thank you for this lecture series. It was really nice and really interesting.
You're welcome. Well, thank you.
We enjoyed it.
I hope that I'm glad you liked it. So thanks. Okay, good. So then that's it for today, and I'll see some of you on. I'll see some of you later. I guess there's one more. Okay, good. So see you.